Thank you. And first of all, I would like to wish the three gentlemen and birthday boys happy birthday, all the best. In particular, health and happiness, and also some more new money. No, I thought theorems and even lemmas or so. No, and of course many happy returns. So happy birthday. And second, I want to mention that what I present here is based on joint works with Karoly Boretsky, and Hannes Polén. And I will speak about the even-dual Minkowski problem, and because I tell you what it is, I will start with the classical Minkowski problem, and I will tell you a little bit the history of this kind of classification problems. I will start, as I said, with the classical Pro Minkovski theory, and here are some notation which I will use. If I have a convex body, so my dimension is n, all my bodies are living in dimension n, then we have seen already the support function of such a body is such a supremum of these linear functions, and the convex body is completely determined as the intersection over all these inequalities. On the right-hand side you have the support function, so you get your convex body. And now there is also, what we have seen already in many talks, there's a nice addition of convex body which is compatible with the support function, namely the classical Minkowski combination. I mean, point-wise addition and multiplication of two sets. This is called, as I said, Minkowski combination. And in particular, the support function of the sum is just the sum of the support functions. Okay? That's a nice simple fact. And so we have an addition. And now we look at a very special addition of two convex body, namely one body, this body M from the former slide, is now the n-dimensional unit ball. So you add k plus lambda times the unit ball, and what you get then is called, will be shown, so later it will be called the outer parallel body at distance lambda. And then what you get, you can describe this also as the set of all points whose closest point, the nearest point in k, denoted by r sub k of x, is at distance at most lambda. Okay, that's also the same Minkowski addition of k plus lambda times the unit ball, and you can describe this via this distance function, say, or with all the points who are at distance at most lambda from k. And this guy, as I said already, is called the outer parallel body at distance lambda. That's a very classical object. And now you can also ask, what is the volume of this outer parallel body? And there is this so-called Steiner formula from 1840. It is just the sum. It is polynomial in lambda. Here you have the binomial coefficients, and then you have some other coefficients, wi, and wi is the so-called ith Kwermers integral. So these are classical functionals. So by the way, here ball always denotes the usual n-dimensional Lebesgue measure. And what do we know about the Kwermers integral? So W naught is just the volume of k, Wn is just the volume of the unit ball, and for instance, n times W1 is just the classical surface area of k. Okay, these are very classical functionals, and there's another, also a very nice interpretation going back to Kubota's formula, so that roughly speaking, the Kwermers integral is just the average volume among all the projections, orthogonal projections of k onto, say, here, i-dimensional linear subspaces. So here you have the Grassmannian. You take the integral with respect to the rotational invariant measure on the Grassmannian. This denotes the orthogonal projection, and this is just the i-dimensional volume. So you can look at it as the average i-dimensional volume. I mean, up to a certain constant here always. I don't care about them. So it is just so the average of the i-dimensional volumes among all projections. That's a nice interpretation of these Kwermers integrals, a very nice geometric interpretation, I think. Okay, so, and now what we do is we are interested in a local formula of this Steiner formula. What does it mean? Local formula means, first of all, I need a notation that we now look at some subsets of the unit sphere. So omega, we take a subset. And now we look at all those points in Rn belonging to the outer parallel body, but they are allowed not to lie in K. So these are points in the outer parallel body at distance lambda, but I avoid points in K. And now the distance between, or the vector between x and the nearest point, normalized to length 1, belongs to the given set omega. Okay, so I'm just interested in all points in the outer parallel body, so that the vector of x to the nearest point, normalized to length 1, lies in the given, say, Borel set omega. So for instance, I hope I did the picture in the right way. This is the set b sub k lambda omega. So here you have a normal vector, or here you have this vector, then, okay, if you take this point, then the nearest point is this point, and of course, this vector then corresponds to this unit vector. Okay, so you have a given set omega, and you just look at the points in the outer parallel body which do not belong to K, and so that the vector between x and the nearest point in K, which is always uniquely determined, normalized to 1, belongs to the given set omega. Okay, you can do it. And then if your set omega is Borel, then again you get a measurable set, and you get a so-called local Steiner formula. Yeah? This goes back to Fenchler and Jessen and Alexandrov. So you can write the same as before. We had the so to global Steiner formula. Now we have a local Steiner formula for any Borel set on the sphere. And what you get here, these coefficients now, depending on k and omega, these coefficients, these Si or S sub n minus I, they are called the ith area measures of the convex body K. This is how you can define them if you want. I mean, there are many different ways. Okay, so just to repeat, so we started with an addition, then we have a volume functional, then we have the outer parallel body, and then we localize the parallel body, and we end up with some measures. And these measures are well known. In particular, if I equals n minus 1, you get the classical surface area measure. So this is, you just take, this is an n minus 1 dimensional Hausdorff measure of all points on the boundary of K having an outer unit normal in omega. So this is something, this eta k to the minus 1 is something like the inverse of the classical Gauss map. If just think at a smooth convex body, then everything is uniquely determined. So this I equals n minus 1, I mean, you have a convex body, and you have a Borel set, and then you look at all the points in the boundary of your convex body, having, let us assume there is always a unique outer normal, so having an outer normal in this set omega, and now you measure this part of the boundary of your convex body. Yes? This is called surface area measure. Well, I mean, just think at a polytope, then it's very easy what the surface area measure is. For a given Borel set, you just sum up some volumes of facets whose outer normal belong to the set omega, right? That's, just think at polytopes, it's very good. I mean, always to think at polytopes, because then one can really imagine what this means. Okay, these are classical measures. I should say, of course, if you plug in the sphere, then again, you get up to a certain factor, you get the Quermass integrals. Okay, so this is a local version somehow of the Quermass integrals, which is clear by the definition. And now, what one wants to know is, which is nowadays called Minkowski-Christoffel problem, one wants to characterize the area measures of a convex body among all finite Borel measures mu on Sn minus 1. So I give you a finite Borel measure on the sphere, and I want to know, is it the ith area measure of a convex body? So is there a convex body such that the ith area measure is the given measure? So you want to characterize, you want to find sufficient and necessary conditions. This is called Minkowski-Christoffel problem, because for I equals n minus 1, this is a classical Minkowski problem. In this continuous setting solved independently by Fenchler and Jessen and Alexandrov, and there's a there's a characterization. If and only, so a given measure is the area is the surface area measure of a convex body if and only if, so to speak, the centroid of the sphere with respect to the measure is the origin. Okay, you just have, here this condition. What does it mean? You know it now, of course. I mean, polytopes are also convex bodies. And as I said already, what does it mean in the discrete case, which was completely solved by Minkowski himself? Well, in the discrete case, it just means, so if you have a polytope with some facets Fi and corresponding outer normals Ui, then roughly speaking, this condition just means that the sum of the outer unit normals weighted by the volume of the facet is 0. Okay? That's a classical identity for polytopes. That this is necessary, it's easy to see. That this is also sufficient is a very nice proof by kind of optimization proof by Minkowski. Okay, for I equals 1, just let me say that this is called the classical, the case I equals 1 is the Christoffel problem. And this was solved independently by Fiery and Berg, but the conditions are not so nice and easy to write down. In all other cases, the problem is open. We are not aware of sufficient and necessary conditions. I mean, we know some necessary conditions, but we are not aware of really a characterization of these area measures. Seems to be a hard problem. Now, one, of course, if you now look at what were the main ingredients so far, we had a kind of addition, we had a volume, and then we had some nice measures. Now, of course, you can ask yourself, what happens if I change some of these parameters? For instance, if I change the classical Minkowski addition by some other addition. And then, as you will see, you get similar problems. And here is one example, namely if you go to the so-called LP Pro Minkovski theory, which was initiated by Fiery and then systematically studied by Ludwig and many others. And here what you do is you replace your normal Minkowski addition by, as I said already, by the P combination. And I just do it here for parameters between 0 and 1. So what you do is here you have a kind of P multiplication and a kind of P addition. And this P is just a positive number. So what you do is here, you just look at the convex body, which is given as this so-called wolf shape. And the right-hand side is given by this kind of P combination of the support function of K and M. Okay? And here 1 minus lambda. This is called P combination of K and M. If there's a difference between P greater or equal 1 and P less than 1, namely if P is greater or equal 1, then here the right-hand side is really the support function of this body. So, but for P less than 1, this is in general not the support function of this convex body. Okay, that's one problem. Okay, this is called P combination. Now you have still the volume functional, so you can compute the volume of this P combination, and then you end up with P Quermass integrals, P mixed volumes, P area measures. And I certainly don't want to go here into the details. I just want to mention that in the classical case, so the classical case is I equals n minus 1 when you have the surface area measure. Then you end up, which is what is called the LP surface area measure. And this has, again, a nice geometric interpretation or representation. You just take here, you take the support function of K to the power 1 minus P, and you just do the integration with respect to the classical surface area measure. Okay. So in particular, as I said, for P equals 1, you always have the classical case, the normal Minkowski combination. So there's, okay. But this allows you, by the way, here to have this representation allows you to have your arbitrary real numbers. Okay, you can also take P equals 0, P less than 0, and this makes sense now. So you have a lot of surface area measures. And then, of course, you have the LP Minkowski problem to characterize the LP surface area measures of a convex body among all finite Borel measures. And for P equals 1, this is a classical Minkowski problem. Roughly speaking, for P greater than 1, this is more or less understood and well solved. For P less than 1, it is pretty much open. And of particular interest is the case p equals 0. Because this has a very nice geometric interpretation. So then here you have p equals 0, you just have the support function. And this problem, the L-not-Minkowski problem, has got his own name. It's called the logarithmic Minkowski problem. And what is now the interpretation of the L-not surface area measure, which is also called cone volume measure of K? Because if you think at a polytope, if you have a polytope again now, with outer unit normals ui and facets fi, and now you look not at the area of the facets, you look at the volume of the cones, given by the convex hull of the origin and the facet. So you have here some cones. And then the cone volume measure, this measure of a polytope, is just the sum of all the volumes of cones having an outer normal in this given set omega. So it's a beautiful, complete, discrete measure. That's why it's called cone volume measure. Maybe you don't see it if you have an arbitrary convex body, but just think at a polytope. We always assume, by the way, that the origin is an interior point here. And everything everything depends a little bit on the location of the origin here. So not always, but yeah, sometimes so. This is called that's the reason why it is called cone volume measure. And there's a beautiful characterization now of the cone volume measure by Borodski, Ludwig, Yang, and Tsang among the finite even Borel measures. Again, yes, you want to characterize always your surface area or LP surface area measures, and they could solve completely the even case in any dimension. And now the statement is that a finite even Borel measure is a cone volume measure of a symmetric convex body. That's the even case, symmetric convex body, if and only if it satisfies so-called subspace concentration condition, which means that the volume is not too much concentrated on a subspace. And the formula is that you require the following: for every linear subspace of any dimension, the measure which is contained in this subspace, it is most the dimension of the subspace over n times the total measure. So it's not too much concentrated. And there's also an equality condition saying that you have equality if and only if there is a complementary space so that the measure is supported either supported on L and L bar. Okay. Yes, it's clear why it is called subspace concentration condition. The measure is not too much concentrated in the subspace. And it's not too much, it's just the dimension of the subspace over n. Very nice and beautiful result. What does it mean, say, by the polytope, this subspace concentration condition? So let us play again with this polytope. Then the cone value measure of a polytope with outer normals ui and corresponding cone volumes satisfies the subspace concentration condition if for every subspace the sum of the volumes having outer normal in this linear subspace L is at most the dimension of L over n times the total volume of your polytope. That's very nice, a simple interpretation. So yeah, you have a polytope. I give you a certain k-dimensional subspace. You look at all the outer normals of the facets of your polytope living in this k-dimensional subspace. You sum up the corresponding cone volumes. And then this cannot be bigger than k over n times the volume of P. This is called the subspace concentration condition. And you have equality. What does it mean now for polytope? Well, in general, that's the same. You have equality if and only if you can write your polytope as Minkowski sum of two other polytopes. You have a kind of decomposition. So that's a clear understanding. And and the general, but unfortunately here the general non-even case of this logarithmic Minkowski problem is pretty much open. Because if you look at symmetric polytopes, then somehow the position of the origin doesn't matter. Because you have here a cone and you have here a cone, and the sum is always the same, independent where the origin is. But of course, if you don't have, somehow you have a kind of translation invariance. If you don't have this in the general case, then it's not clear what to do. And of course, in general, if your origin is very close to the boundary, then the polytope does not satisfy or the convex body does not satisfy such a subspace concentration condition. So everything depends on the location somehow here in the non-even case of the origin. There are a lot of results in the non-even case. For instance, it was very much studied by Alina Stanko in the discrete case. And she proved, among others, that if you have a discrete now, a measure, and satisfying this subspace concentration condition, then you can find a polygon corresponding to this measure. But no, there's no statement about the position of the origin. Then this was solved for discrete measures in general positions. You assume that among, so to speak, among the normals, you're looking for a polytope so that among the normals, n of them are always linear independent. There is a generalization as a sufficient condition in the discrete case by Borodski, Hegedüs, and Zhu. There are necessary conditions for so-called centroid convex bodies in a joint work with Curley, where centroid means we assume that the centroid is at the origin. And there's also a recent preprint by Chen, Li, and Zhu about sufficient conditions. The only problem is that the sufficient conditions do not match the necessary conditions. It is not clear. I mean, even for polytopes, it's not clear what is the right characterization. So, I mean, of course, for me at least, one obvious approach would be I'm just interested in polytopes having the centroid at the origin. And I want to give because it's generalized nicely, the central symmetric case and to the non-even case. And but there it is not known how to characterize the cone volume measure. Okay. So this is just a little bit about the cone volume measure, which is a quite important measure in modern convex geometry, and it appears in many different contexts. So now I come to the dual Minkowski problem. We had somehow the primal Minkowski problem, the classical one. We had the LP Minkowski problem. And now we come to the dual Pro Minkovski theory and the dual Minkowski problem. And this again goes back to Erwin Ludwig. And again, the idea is you take convex bodies, you change the addition, you apply the volume functional, and you look what you get. And here now, the addition is based on the radial function. So we replace the support function somehow by the radial function. So K is a convex body, the origin is in the interior. Then the radial function is just the maximal rho such that rho times x belongs to K. That's a radial function. In particular, K is now given by all the points having radial function at least 1. This is K now. You can describe K in this way as in this, let's say, primal case with the support function. There's a close relation between the radial function and the support function. The radial function is just the inverse of the support function with respect to the polar body. Okay, that's. And now we look at the radial addition. And the radial addition for two vectors is quite easy. It is either 0 if the vectors are linearly independent, the two vectors, or it is just a sum. Okay, that's a very simple addition of 2 points. If they are linearly independent, you sum them up, and otherwise it is 0. So if they look in the same direction, you just take the sum, otherwise it is 0. And now you do the radial combination. And the radial combination is just of two convex bodies, of whatever actually, of two sets of convex bodies Km and positive numbers. It's just the radial addition of all the vectors. For instance, here if you take K and the radial addition with minus K, you get such a guy. It doesn't look too convex, but that's actually, it's a star body. You always get a star body. You can apply the whole theory with respect to star bodies, and that's actually not a bug, that's more a feature of the whole theory, that you can extend it to the sets of star bodies. So this is now the radial combination. And again, this radial combination is compatible with the radial function as the support function with the classical Minkowski addition. Okay, now you can define again the dual outer parallel body as in the classical case, but now with respect to the radial distance. Yeah, you look now at all the points, either they belong to K or they don't belong to K, and the radial distance is at most lambda. So the point here, the radial distance, just you have a point, and you look at the intersection with outside of K, and you look at just at the section of the ray from the origin to this point where it hits the boundary of K. Now you have the radial distance of K, which is at most lambda. So you have a radial dual outer parallel body. And there's also a dual Steiner formula, going back to Erwin Ludwig. The same as in the classical case, and here you get now dual Quermass integrals, denoted by tilde Wi. And there's also, okay, you have again the volumes, and there's also a kind of dual Kubota formula. So now these dual Quermass integrals are not the projections, the average of all the projections, but they are the average of all the sections with linear subspaces. So you have many similarities or dualities between this dual Pro Minkovski theory and the classical Pro Minkovski theory. Yes. Now, this dual Pro Minkovski theory is now an essential part of modern convex geometry. It appears as in the theory of intersection bodies. It plays a fundamental role in the final solution of the Boseman-Petit problem, and now in the more isomorphic Boseman-Petit problem. It shows up, this dual Pro Minkovski theory and the dual Quermass integrals also in the famous and well-known slicing problem or in the isotropic constant. So it is really something essential in convex geometry. And there are certainly many more applications of this. Now, what was missing for a while, if you look at this classical Minkowski theory, there we have the surface area measure coming from this localized outer parallel body. And these measures were somehow missing in the dual Pro Minkovski theory. And this missing link was really established by Huang, Ludwig, Yang, and Zhang. Namely, they also introduced a local dual outer parallel body with respect now to this radial function. So this is now the set A tilde. So again, we take a subset of the sphere, we take our convex body, and now we look at all the points whose radial distance is most lambda. So again, we have a subset of the dual outer parallel body. But now the radial nearest point, this is this guy, has to belong again to the given set nk to the minus 1 omega. So at this point, we demand that this point has a supporting hyperplane with outer normal belonging to omega. Okay? That's the definition of a local dual outer parallel body. Again, I just want to stress that it is quite similar. The steps are similar to the classical theory. Okay, you have a outer parallel body, and now you look at the proper local version of it. And then you look at the volume of these local dual outer parallel bodies, and for a given Borel set, they are measurable, and again you get such a polynomial. And now these guys here, these coefficients, they correspond to the surface area measure, but now they are called ith dual curvature measures. These tilde Cik of omega. Okay. And they are very interesting. First of all, as you can expect, that if you plug in the sphere, then you just get the dual Quermass integrals. But they also have a very nice explicit representation. To this end, I need one more set. This is just this set alpha stay k of omega. You just look again at all the points in the sphere, so that rho ku of u belongs to this inverse of the Gauss map. It's not so important what it is, but if you have this set, you can really explicitly write down an integral formula for these curvature measures. Dual curvature measures. So what you do is you take this set here, you take the integration over the set, and then you take the radial function to the power q. Okay, and then here you have this factor 1 over n. And this again, like for the surface area measures, this again makes sense for any real Q, this formula. And yeah, and the surprising thing now is that if you plug in Q equals n, then you get this beautiful cone volume measure, which was, at least for me, quite surprising that you also end up in this way with a cone volume measure, at least for Q equals n. And there's another known measure. This is the so-called integral curvature measure of Alexandrov. And this is what you get if you plug in Q equals 0, but with respect to the polar body. Anyway, it is very surprising to see that there is a sequence of measures combining these two measures somehow. That's it. So the dual curvature measures say somehow, at least between 0 and n, they interpolate between the integral curvature of the polar and the cone volume measure of K. So whatever you can say about the dual curvature measures, for general Q, it should be also then, of course, in particular for Q equals n, it gives you something about the cone volume measure. And the dual Minkowski problem is now just the classical characterization problem for measures with respect to these dual curvature measures. You want to find necessary and sufficient conditions for the existence of a convex body K so that this Qth dual curvature measure is equal to mu. Okay, and in particular for Q equals n, you get the logarithmic Minkowski problem. Now, what is known? I mean, these measures are rather new. Not so much is known. In this paper by Huang, Ludwig, Yang, and Zhang, they proved a sufficient condition, which doesn't look too nice. But again, of course, it's a generalization or an extension of the cone volume measure. So you are looking for subspace concentration conditions. And they proved that if you have a measure on the sphere satisfying such a subspace concentration condition, then it is the Qth dual curvature measure of a symmetric convex body. So this was sufficiency. And in particular, for Q between 0 and 1, this is also necessary, but then this number here is negative, so you get here just a 1, and this means you just want to avoid any kind of concentration on a great circle, or yes. So this is clear that this is also necessary. And also, if you plug in Q equals n, then you get exactly this subspace concentration condition from the logarithmic Minkowski problem. So this was really a very nice result. But then it turns out that this is not the right number somehow. Namely, then in a paper with Cauchy and Hannes, we could prove the following necessary conditions. That if K is a symmetric convex body and L is a proper subspace, then you get here this number, which looks a bit more simple. So this is just a dimension of L over Q in general, if the dimension of L is not bigger than Q. And then maybe almost at the same time, and then in particular, this was shown by Yiming Zhao, this was shown to be also sufficient, this number, as long as Q is an integer between 0 or between 1 and n. And recently, this was extended to all numbers by Boretsky, Ludwig, Yang, and Zhang, and again Zhao in a recent result. So now we know that these are really sufficient and necessary conditions for, in the even case, for the dual curvature measure. Okay. Yeah, and what is else known? In another paper, as I said, these dual curvature measures are, they make sense for any real number Q. And then it was also, there's a result again, another result by Yiming Zhao, settling the case when Q is a negative number. Then you don't have you have just a trivial subspace concentration condition, namely mu is not concentrated on any closed hemisphere, which makes sense for such a measure coming from a convex body. And he also could prove the convex body is uniquely determined by the measure. And then recently what we were able to do in a joint work with Hannes Polén is to prove necessary conditions if Q is greater or equal n plus 1. And this bound is also best possible, okay? That you have for every subspace now for QE greater or equal n plus 1. So what remains open for necessary condition is the case Q greater n and less than n plus 1. And I want to briefly point out, I think, why we cannot do it. By the way, we can fill the gap in the two-dimensional case, but this is a special trick and a special approach. Okay? So let me give you the details. I mean, what you want to do is you want to, and just think about polytopes. So whenever we try to prove something about this, we think at polytopes, because then it's somehow, the picture is more clear, at least for me. So suppose we have now a Q greater 0, then we can write this dual curvature measure in this way. So instead of the radial function, I just take the Euclidean norm to the power q minus n. And again, I have here this set. What does it mean now for a polytope? Again, I take a polytope, and then here I just have I take this measure, I take the sum over all normals belonging to the set omega, and then I have this integral over the cones. So it's a clear geometric integral. So I have here a certain number and want to evaluate this power, Euclidean norm to the q minus n over this cone. Okay? How to do this? Well, I mean, do you draw a picture? So imagine that this is your set, and you have here such a cone, and you want to do this integral. I mean, you cannot avoid to do it explicitly, forget it. I mean, because you take some power of the Euclidean norm, there doesn't make sense. But of course, if you have each integral depends only on the integral of the facet by homogeneity. So you can everything rewrite as a proper integral over the facet. Okay? And this is here, suppose that's a picture. Here's L, here's our orthogonal complement. So we are in a one-dimensional case, say L is a one-dimensional plane. Okay, so this guy can easily be evaluated. I mean, we can rewrite it somehow as an integral over this facet. That's all. But now we have, on the other hand, we have to compare it to the total dual curvature measure. And of course, we can write this by Fubini or Cavalieri or whatever, or whoever. As such an integral, we go over the projections, and then we look at the sections, I mean, perpendicular to L, right? Okay, that's what, you can do it. And then you observe that each slice here, if you take such a slice or here such a slice, now we are in the even case. So here we have fi and here we have minus fi. Then of course you know that each slice here, roughly speaking, contains 1 minus lambda times fi plus lambda times minus fi. So again, a set which depends on fi. Okay, and so you want to compare the integral over this slice with the integral over such a facet. And this reminds you, of course, to Pro Minkovski. Because if I just take q equal to n, then I mean I just compare the volume to somehow to the volume here. And this is what we need. So we need a kind of Pro Minkovski type estimate, but now for such an integral. Okay. And if this q now is not bigger than n, so if q is not bigger than n, this function here is a even, of course it's even, a quasi-concave function. This means all the super-level sets are symmetric convex sets, and then you play a little bit with the integrals, and you apply Pro Minkovski to the level sets. And then is what you get in general. So if you have a compact convex set, dimension of k, you take a hk measurable even quasi-concave function, then you get such a Pro Minkovski type inequality with m and minus m. Okay? This is exactly what you need in the case if q is not bigger than n. Well, if q is greater or equal to n, then it's more difficult. And here's what we could prove, and we cannot prove it for quasi-convex function in general, or even for convex function we cannot prove it. We just can prove it for the norm. So here's a general statement. It says, I give you two compact convex sets. Both of them have the same dimension. They have the same k-dimensional volume. And I look at the Minkowski combination k lambda. It's 1 minus lambda k naught plus lambda k1. Then for p greater equal 1, you get the integral of the pth moment of the Euclidean norm plus the integral of the pth moment of k1 minus lambda gives you this in terms of the pth moment with respect to k0 and pth moment with respect to k1. We can also completely characterize the equality case, but for p equals 1, I don't write it down because it's much more involved to characterize. Because this is exactly where you go from quasi-convex to convex. And that's why we cannot do it for p less than 1. It's not true, by the way, such a formula. Okay, and this, of course, implies what we need, that if q is greater or equal n minus 1, then our exponent, this p, is greater or equal 1. And then we get exactly such a Pro Minkovski type inequality with this factor here. That's a weak Pro Minkovski type inequality. But this is best possible. You cannot get more. Yeah, so that's, and then if you use this, you get actually what you want. By the way, the proof of this Pro Minkovski type inequality, or weak Pro Minkovski type inequality, it took us some time to find it. We were also not sure whether the statement itself is true. What we use is a nice reinterpretation of the pth moment as the average over, as such an average over the sphere of the distance of points from a hyperplane, which was first, we found it, the first reference we found in a paper by Alaska, but it was also used in the work of Pauris. What you then apply is a kind of inductive proof of Pro Minkovski, which goes back to Kneser and Süß, via slices, the corresponding slices. And then at the end, you apply an inequality which is known as Karamata inequality, but it also goes under the name Hardy-Littlewood-Polya inequality, or Weil inequality, or Siegel inequality, or Schuh inequality. It's about if you have two vectors and x is majorizing in a certain way y, and you have a non-decreasing convex function, then you have such an inequality again. So some people call it Hardy-Littlewood-Polya or Karamata inequality. And if you put all the things together, and then you get what you want. Then you get this weak Pro Minkovski type inequality. Well, there are more things to do. Of course, as I said, we cannot do it for q between n and n plus 1. I mean, this Alaska and Pauris stuff, that's also true for p less than 1. But this Karamata, for instance, it's not true, because there you need really convex, you need p greater or equal 1. And we also know that this Pro Minkovski stuff is not true for, I mean, in general, what we write down for p less than 1. But we use a completely local proof method. We localize. So in the average, at the end, we do integration. This doesn't mean that it is not true at the end, but just our proof doesn't work this way. And of course, you can ask whether this constant condition is also sufficient. It's not clear. And in the non-symmetric case, I have no idea, and we have no idea how to do it. Thank you for your attention.